Hi there. So due to some popular demand for walking through some sample problems, not just the posted solution, I'm going to be going over one circular motion problem and one or two gravity problems from our notebook. And so this is problem 5 from page 140 in the textbook. And we're told that we have this flat puck of mass m, big M, capital M, and it's going in a circle, so it looks kind of like an oval here. We're just kind of looking at it from kind of a skewed perspective on a frictionless air hockey table. So that's pretty nice. Mu is 0. And it's held in this orbit by a light cord, which is connected to a dangling mass, little m. So here's our little m, and here's kind of the cord. And so since it goes in the same circle, this radius doesn't change. Whether the puck's over here, it's still the same length of this light cord that goes down. And it goes through the central hole, and we're told that we need to show the speed of the puck is given by this. So really, they're giving us the answer here and saying, can you prove it? Well, first thing to do, I would say, is let's start with the easiest thing. Just looking at our diagram here, I can see that our mass is getting pulled down. That should be an arrow a little more vertical, but that's okay. Down by gravity, and tension is pulling up on it. And similarly, if we looked at our kind of big hockey puck here, there must be some tension going along here. If there was no force acting on our puck, well, the puck would just fly off tangent. If the string broke, the puck would just fly off tangent to the circle with whatever speed, velocity it had. In the case of this one, though, looking at our smaller mass, little m here, I can see that, well, since the puck is at the same radius the whole time, so the length of string up top here isn't changing, big R isn't changing, that means this smaller mass must really be kind of floating in the air. It's kind of staying at the same position forever, at least as long as this little puck is rotating. So that tells me here that our force of tension is equal to the force of gravity. And the force of gravity we could rewrite as like little m g if we so wanted. Now, when it comes to looking at the big puck here, and again, the goal is we're trying to like prove this equation. And so we're trying to figure out how can we kind of relate some things. What do we have to really work with? Now, in looking at the puck here, well, the tension, if the puck was over here, the tension would still be pointing towards the center. If the puck was over here, the tension would still be pointing towards the center. So I would argue and say that the puck is the centripetal force. Now, I think here it's a good kind of aside to mention that for things going in circles, whether it's a puck going around a table, this could be us looking vertically down on the puck as it spins around kind of the little hole right here. There is tension, and tension is always acting towards the center. That means that in this case, tension is the centripetal force. It's not that there's two separate forces. There isn't some mystical centripetal force that's always pointing towards the center, and then there's tension. That's not true. They're not two separate forces. Tension is the center-seeking force here, which we call the centripetal force. Now, if this changed and it was, I don't know, the sun, and now we had this was the Earth kind of going around the sun, well, it wouldn't be tension keeping it in orbit. It would be the force of gravity here, is kind of the idea. And so we could set those two equal because gravity is the center-seeking force here. Gravity would always be pointing towards the center. And we could plug in and substitute for Newton's universal law of gravity and do things. But that's kind of an aside, and let's go back to our problem here. So in the case of this, we have tension is our center-seeking force. So I want to do a little highlighting. Tension is the center-seeking force, but tension is also equal to the force of gravity. So what that tells me then, if tension is equal to the centripetal force and tension is equal to gravity, I can set those two equal. And so I can go ahead here and say that, oh, well, force centripetal equals force of gravity. Now, an important distinction, though, here is that the centripetal force is on the big mass. The force of gravity is on the little mass. And so now we can go ahead and we can plug in, and we would say that m or it would be big M times V squared over big R, I'm trying to use the same symbols that are given in the problem, is equal to little m times G. And so now if I kind of clear up a little space here, we could kind of do a little algebra, kind of tidying up, because the goal is we want to find this speed. We want to prove that the speed is this. So I want to get V squared alone. And so keeping V squared alone, I'd have to multiply by R and divide by big M. And so I would have this mg, but then I'd be dividing by big M, I said, and multiplying by big R. And so then I just need to take a square root. And so if we square root the left side, well, we get the velocity. If I square root the right side, well, we end up having the square root of mg big R over m. And we can see here that this value is in fact the same as the answer they want us to prove. And so that's how this was done, by really looking at what are the forces at play here and what can be set equal to it. Okay, fantastic. Now, similarly, let's go ahead and look at a couple gravity problems. At least one, maybe two. Too far, sorry about that. Let's look right here. Fantastic. So we have a man, and he appears to be in a cylindrical spaceship. And we're given the picture for it. We kind of have a diagram. Here he is. He's kind of just chilling here, looking in it. And it's saying at what rate. Now, what rate? That's like, what rate am I traveling? What rate am I reading a book? That's usually the speed. That's usually quickness, kind of things like that. So I put V here because that makes me think, like, how quickly does it need to rotate? So at what rate must this cylindrical spaceship in the picture here rotate if occupants are to experience simulated gravity of 1/2 G? So we want to have half the force of gravity is what they want to experience. Assume the ship's diameter is 32 meters and give your answer as the time needed for one revolution. Well, the time needed for one revolution, that's big T. That is usually our period. So really we're trying to find the period that needs to kind of that the ship needs to rotate in to give us this 0.5 or 1/2 G. And so maybe that sounds like a lot. And we're going, well, what is going on here? Well, I think when I'm looking at this immediately right here, well, I can see that there's a man and he's being pressed against essentially the floor, which becomes the ceiling later on, of this cylindrical spaceship. So there is totally like a normal force here. And it's actually essentially the interior of the cylindrical shell pushing up on him, and it's always pushing towards the center, which is kind of odd. So this normal force really is pushing towards the center right here at kind of all times along the axis that it spins. And we want to end up getting that this centripetal force that's caused by the normal force is 1/2 of G. So I've already gone ahead and said, well, we need this center-seeking force that he experiences to be, well, half of gravity. And so how can I go ahead and figure that out now? Well, it's asking for the rate that we need the speed. And I know from my kind of math classes that speed is this 2 pi r over t, because the distance is the circumference of the circle here. So it's 2 pi r, and the time to go around once is t. And this is helpful because it's asking us to get it kind of in these terms here. And so we know the radius, we know exactly what that is. And so what we can do now is we can actually just set that the centripetal acceleration, because we want 1/2 of gravity to be experienced, we can set the centripetal acceleration equal to 1/2 of G. And this is helpful, but it's helpful only as long as we remember that the centripetal acceleration is equal to V squared over R. That's really what we're asking for here. And we can go ahead and take this version of speed and we could plug it in here, is what we'll actually be doing. And so I went ahead and I said that, well, now I can know that our centripetal acceleration is this V squared over R. And we know that we want the centripetal acceleration to be 1/2 of gravity. So if the acceleration is equal to the green here, but the acceleration is equal to the red, I can set my red and green equal to each other. This is where this actually becomes helpful, but we had to be able to kind of make this connection and then this connection and then set the two right sides equal to each other. With that being the case, I now can finally, as I said earlier up here, we can take this version for speed and we can plug it in to this left-hand side for my speed. And so I went ahead and I'm showing all my steps here. We have 2 pi r over big T, and that's squared over r is equal to 1/2 our kind of gravitational acceleration we want, 1/2 g. And maybe at this point you're going, what are we doing? Why do we care here? Well, again, we want to find out the rate, how quickly this shell of the spaceship has to rotate for this person to experience 1/2 g. And we want to know how quickly they have to rotate in terms of the time for it to do 1 revolution. If it did a revolution faster, they'd be experiencing more than 1/2 g. If they did a revolution slower, they'd be experiencing less than 1/2 g. And so in this case, we're really just trying to go ahead and get this big T alone now, and we have to kind of do and slog through a little bit of algebra here. And so what I've done is I recognized that this becomes an r squared, and there's an r squared divided by r. So this r goes away, and then this top r is no longer squared. And then everything else was just 2 squared is 4, pi squared is pi squared, t squared is t squared. So I have that. And then I have my right-hand side. And then I just went and I've gotten t squared alone. So I multiplied t squared over to the right side, and then I got rid of the 2 by multiplying it over to the left, and I even divided by g. And so I now have this kind of form here, and maybe you might need to show a little bit more steps for yours. But then with all of that, I just had to take a square root of this left-hand side, and then I have my period. And luckily enough for us, we know what g is, and we were given the radius is this 32 meters. And so I was able to go and actually plug into this equation here, and 8 and pi squared, and we were given the diameter. The diameter was 32 meters, so that means the radius is the 16. And once we kind of go through and poke this into a calculator, we get 11 seconds. And so if it spins at 11 seconds per entire revolution, the person would experience 1 g. If it spun quicker, so if the time was 10 seconds, it would be going too fast. It would have more than 1/2 g. And if it was going slower, so if it took like 12 or 14 or something longer seconds, they would experience less than 1/2 of g. And so really this was kind of more of a, how do we pull apart the important things from the problem and then set them equal kind of question really than anything else, and then a check for algebra. And I would say that kind of the big key step is recognizing that the acceleration is this, but we also know that the acceleration is this, so we can set those two really equal to each other, was kind of the big step here. And just because I also would like to look at which one is more helpful, I think. I would say problem 48 here. What's a procedure to determine the mass of a planet from observations on the orbit of one of its satellites? So we want to find the mass of a planet. That's really what it's asking us here. Determine the mass of a planet. Well, if we want to find the mass of a planet, we probably are going to be using Newton's universal law of gravity. We likely will be using this big guy here that has the mass of the planet and the mass of the satellite kind of at play. Now, if we're talking about the orbit of its satellites, though, well, gravity's keeping the satellite in this orbit. I've kind of sketched a little picture here, kind of showing it all. Well, if that's the case, gravity is what's keeping this satellite in orbit, and so we know that there must be a centripetal force then, and it is gravity. Gravity is the centripetal force on the satellite, and it depends on the mass of the satellite. So I'm going to, since my picture here had the satellite as M2, I'm using M2 in the centripetal force equation, times that acceleration, which we just looked at in the previous problem, is v squared over r. So we want to find the mass of the planet. Well, if I want to find the mass of the planet, that would be M1. Well, I want to find M1 then. How can we go about doing this? Well, I see that if we can set the two of these equal to each other. And I'm going to switch over and actually look here. I set them equal to each other. And then I went and I just kind of rewrote the right-hand side versions of each. We already had the left-hand side version written. We can see that a lot of these things cancel. M2s cancel, we have an R cancel on the left side, and there's no R anymore on the right side. And then I can just do some algebra and get M1 alone. And you're going, okay, how does that help? We want a general procedure to find the mass. Well, when I look at this equation now, all this equation is really asking us to find is the radius and the speed of the satellite. So we'll have to unpack this speed part a little more, because we know that the speed depends on the circumference and the period. And so what this really boils down to is, if our person, or you, or an astronomer, were to watch the satellite orbiting, and they could get the period until it goes one full circle back to the same spot, we would know the period. If they also could determine the radius of the orbit. So we know not just the period, we know the radius. If we know the period and the radius, we could absolutely plug in and find the speed. And then we would know the radius again in this equation, and we would know the speed, we know the radius, we always know this universal constant, and they would be able to find the planet's mass alone. I took this a step farther and I plugged in V into, I took V and I plugged it into this equation, and that's what I've rewritten here, is this big kind of gnarly looking formula, but it's the same thing. It's the same idea as saying, if we can find the speed, we could just plug it in to this guy. And that's really what the observations would need to be. So the procedure would be, find the radius and period of the orbit. We could use these to find the speed of the satellite, and now we have enough information to set the force of gravity equal to the centripetal force, and that would let us get the planet's mass. But it really took me not just thinking hard about it, it took me going through and actually seeing what can I set equal, and kind of going through and coming up with a helpful equation that allowed for this all to be done. So I hope that made sense. I will just mention that for problem 49 here, the centripetal force, you totally have to use the radius, because there's two stars and they're orbiting like around this little center dot here. So the centripetal force is just what you would expect. It's, well, mv squared over r. But the force of gravity, there's nothing actually here. So the force of gravity is from one star to the other, because they're orbiting each other. And so you will have to use not one r as the radius, they are 2r apart from each other, because there's r and there's r again. So you'll have to use 2r for your radius in Newton's universal law of gravity once you set those equal.